Okay, this is a quick video about how to calculate the center of mass. It's not a video about why center of mass is an interesting concept or extremely useful to physicists or about conservation of momentum. I just want to know, what is this? What is this? How do I use it? When do I use it? Okay, first of all, let me just say that this is an average. Essentially, you want to know, on average, where is all the mass in your system? For a continuous distribution, you look at something that looks like this. One thing I'll point out, this is a vector because it tells you a set of coordinates. There's an XCM, a YCM, and a ZCM. In other words, I want to be able to point in space to where the average location of all the mass is. So what I'm finding is a vector XCM that has those as its coordinates. Okay, so let's set this up. We'll see how we use it. This is going to be a rather calculational video. It's not particularly interesting, but I think it'll be useful and it'll help you solve some of the problems you get. Okay, so let's look at the easiest case. 1D particles. Okay, that means there's no y or z direction. There's only x's, and so if I want to apply this formula, really what I'm looking at is adding up each of the individual masses and their actual position. So that is, I only have x's to consider here, and I add them all up. So let me just show you what that looks like. This guy is m, and it's at 0. So I put m times 0, m1, x1. This guy is 2m, and it's at x equals 2, 2m, 2. And in the bottom, I just add up all the masses. You get the idea. If I do all that, I'll end up with x equals 3.6. What does that mean, 3.6? Well, that's the average of where all the mass is. That's somewhere around here. And actually, yeah, that kind of makes sense because I've got a lot more mass, 5m, over here than I have over here. If it bothers you that it's 0 here, and you're like, wait a minute, it's like you're not counting it. No, I am counting it because it's weighting it more towards 0. It's making it a smaller number. So this is on average where the mass of my system is. That's what the center of mass is. Let's look at a more complicated example. Okay, now we're in 2 dimensions. Oh boy. It's actually the exact same problem. I just have to do it twice. When I do this, notice that the center of mass in the x direction only cares about x's, and the center of mass in the y direction only cares about y's. So when I go to calculate these things, even though there's 2 numbers here, when I do the x's, I only care about the x coordinates. I only care about the x coordinates. And when I do this one, I only care about the y coordinates. This, if you understand the other one, is basically the same problem. There's really not much new to talk about here. Okay, let's calculate it out. We get a final answer. We get a coordinate, right? 3.1.6. What does that mean? That's somewhere around there. Well, if you think about it, most of the mass is around here, and so this makes it lower, this makes it higher, this makes it lefter, this makes it righter, and this guy wins more than the others. So yeah, that's about it. That's where the center of mass is and how you calculate it. So now let's get crazy. Okay, here we go. 1D continuous. So here's my formula. It should still work. The problem now is I have one end at x equals 7 and one end at x equals 2. I never had that before. I always said that the particle was in one place. Now it's in 2 places. What do I do? This is a bit of a problem. So what I'm going to do instead is I'm going to say this bar is not really one thing. This bar is lots of little things. And I'm going to add up all of those little things together. And I'm allowed to do that so long as I keep the little things very small. In other words, if I make this piece so small, its left edge and right edge don't really have different positions. It's essentially in the same place. If that bothers you, think about what you did in your calculus class. That's actually the claim you make all the time. In the limit that dx approaches 0, you say that some function has the same height at 2 different values of x, so long as they're dx apart. I'm just saying the same thing. The distance along the rod is the same on both ends of these, so long as I allow dx to be really small. Of course, if I have a very small dx, I'm going to end up with a very small dm. Another way to say that is that dm is mass per unit length times length, right? Well, I'll have a really teensy bit of mass if I have a teensy bit of length. This guy lambda is a bit of notation, totally standard, what physicists like to call mass per unit length. Lambda sounds like length, so we use that. For area and density we use, and volume density we use other Greek letters, which I'll show you in a second, but it's really just a bit of notation. Okay, so what do? We have to make a bunch of these little things and talk about each little bit of dm at each different x, and then we add them up. Only instead of m sub I, they're dm's. They're all the same mass and they're all really tiny. and I have some variable that changes. If you think about this, though, you're going to have to add up an awful lot of these, in fact, an infinite number of them, and doing an infinite sum is a drag. Fortunately, somebody figured out a quick way to do it, and that's called an integral. Apparently, an antiderivative is the same thing as an infinite sum. You learned that in your calc class, of course, right? Okay, so what do? I just plugged in for dm. Instead of dm, I wrote lambda dx. Up here, I need to multiply by an x because there's an x here, so I threw an extra x up top. On the bottom, it's just the integral over dm, so I just plug in lambda dx. Okay, so this gives some number. Now you might say, wait a minute, what's lambda? What do I do about lambda? Okay, there are two cases. One is which the bar is uniform, in which case I have a value of lambda here, and I have a value of lambda here, and it's the same. The bar looks the same everywhere. So if I want to know how much mass per unit length there is, it doesn't matter. I take the total mass, divide it by the total length, and it's just some number. The other case is it's not uniform. And if it's not uniform, somebody needs to tell you something about the bar. You can't just say, go find the center of mass of this non-uniform bar. You'd say, well, how is it not uniform? In what way, right? I'll talk more in maybe another video about how you don't even need to do math in order to find the center of mass of a crazy bar, but that's a different topic. Okay, let me show you two examples side by side. One, the bar is uniform, the other bar is not uniform. This is what the problems would look like. Okay, find the center of mass of a uniform rod of length 5 meters and mass 10 kg. And this one, find the center of mass of a rod that's 5 meters long but has a non-constant density. Okay, so what I'm going to do, I'm going to get rid of the numbers and just put an M and an L because I don't feel like doing numbers anymore. And I'll just say lambda is total mass divided by total length, M over L. So what do? I plug in for lambda, I shove in my x, that's all I'm doing, lambda x dx. Where do I integrate from? Well, I go from x1 to x2, but I think it'll be instructive. Let's just pretend that x1 is 0. And if the bar is length L, that would make x2 L. And so I go 0 to L on both integrals. I do the same exact procedure here, except instead of plugging in M over L, I plug in x squared. So it's lambda x squared times x. You get x cubed. Okay, if I do this, I'll get L over 2 here, and I'll get 3L over 4 here. Does that make sense? Well, if it's uniform, where do you expect the center to be? Center of mass should be in the center. That's the average location. If it's non-uniform and the mass gets bigger, in other words, this thing maybe gets heavier and fatter as I get toward this end because it increases like x, well, then yeah, I expect to find it closer to that end. So this makes sense. This is about as hard as it gets when you're in one dimension. They can give you weird integrals to do, but from a physicist's point of view, I just plug it into your favorite online integrator. It doesn't matter. Okay, now it's going to get real. This is where things start to get a little difficult. There's a limited number of cases of this that we can look at in a class where you're not required to know multivariable calculus. I'm going to show you the formula you come up with, and if you know multivariable calculus and that's your thing, you are set. You can go to town doing double and triple integrals. If you don't like double and triple integrals, I'm going to show you a couple of examples that you can do without knowing multivariable calculus, even though technically that's what you're doing. Okay, so this formula still applies. So I still need to know dm, and dm looks different. If it's a area, then dm is mass per unit area times area. If it's a volume, then it's mass per unit volume times volume. In other words, instead of breaking up a line into tiny slices of a line, a cube is made of tiny cubes. Each cube has a mass dm. A square is made of tiny squares, and each square has a mass dm. So what does that look like? Here, dm is sigma, so that's what we use when we talk about the mass per unit length, mass per unit area, excuse me, that's just a bit of notation. And then rho is what physicists like to use when we talk about mass per unit volume. So strictly notation there. And then what's volume? Dx, dy, dz, because I have to go this way, and I have to go this way, so I'm adding up the wrong dx, and then I have to go into the cube. I have to go in this direction too. I have to do all three directions. And so this sets me up in a position where for this guy, I need 3 integrals. And for this guy, I'm going along this direction. I got to add up all the boxes, and then I got to add up all the boxes in this direction. I got to do an integral that way too. So yes, you have double and triple integrals. They don't look pleasant. The truth is there's a lot of cases you can do without really even understanding what these triple integrals are. I'm going to switch up the notation really quickly one more time just to make it a little easier to write, but also just to say it's not so much dy, dx, dy I'm interested in. What I want to know is what is dA, the area of that? And the reason I do that is I don't know if I have a sphere and I want to work in spherical coordinates. Well, maybe I don't want to use dx, dy anymore. I can use spherical coordinates. More than that, though, for these next two problems, I'm going to show you what I really mean when I say it's dA that's important, not dx dy. Okay, so here we go. I've got two examples. One of them is a 2D example and the other is a 3D example. For the 2D example, it's an inclined plane. What would a physics video be without an inclined plane? So we'll try and find the center of mass of this. And just as a quick guess, you might say, look, there's less material on the top half than there is on the bottom half, so it's probably below the middle of it. And then over here, I've got a pyramid, and this is interesting. So for this guy, the inclined plane, I have constant density. For this guy, I have not constant density. For this guy, I say the density increases as I go up, but there's also less volume as I go up. So I'm not sure who's going to win here. There's some halfway point, and I don't know. I have to calculate whether it's going to be above or below. Okay, so let's see how this works. Okay, the thing I've got to do is the thing I always have to do, which is I got to figure out what this dm is. So dm is sigma dA. What is dA? What do I do for dA? Okay, one idea is that I could say that I could build the whole area out of little areas. In other words, if I take a bunch of little rectangles and I find the area of each one, then I can find the area of the whole thing by adding up all of the rectangles. What's the area of each rectangle? Well, each rectangle has a length and it has a height, dy, and so that's dA. So what does it look like? I can say dm is sigma dA, and then I just punch in sigma. Piece of cake. There is one awkward thing to talk about, though, and that is that I'm integrating over y and I've got an x here. That's a big no-no because x and y depend on each other. So I've either got to get rid of the dy or get rid of the x. So I'm going to get rid of the x. So how do I get x in terms of y? Well, I know that on an inclined plane, this is a straight line. So I know that the x changes linearly with the y. In fact, x looks like y cotan theta. That's the equation of a line. It has a negative slope because it goes downward, right? But the other thing to consider is that when I'm at the bottom, x should be L. So when y is 0, x should be L. When I get to the top, x needs to be 0. So x gets smaller and smaller as I get higher and higher, and this does it. You can pause the video and stare at the diagram if you want to look at that further. What we do with this is just punch it in. In other words, instead of putting an x, I now put that term in. And what do I do with this? I punch it into these formulas I've been using the whole time. And so all I'm going to do for the top integral is I'm going to have a sigma. I'm going to have a sigma in the top integral. Multiply it by a x and then see what shakes out of that. And then in the bottom, I'm going to multiply it by a y. So let's see what that looks like. So, okay, here I have this term. It's squared because I had to multiply by an additional x. Down here, there's still only one of those, but there's a y there instead. I don't know what these integrals work out to. I don't particularly care to do them. You can do them to figure it out and figure out if indeed the center of mass is below the midpoint as we expect it to be. One thing you might wonder is, wait a minute, what are the limits on the integral? Well, okay, look, you're starting at 0 and you're going to this, L tan theta, whatever it is. So if you want to integrate by hand, feel free. If you want to punch it into an integrator, that's fine too. All right, let's move on. What happens in this case? Okay, here we've got a non-linear density that we need to worry about, a non-constant density. So here our job is to find dV. How do we find dV for this? Almost the exact same way we did for this, except instead of using rectangles, I'm going to use little cubes. That is a smushed up little cube. It is a square, and the square has some little tiny height, dz. And as the squares get toward the top, the squares get smaller, just like the rectangle gets smaller. And so we'll have to figure that out at some point. But the key is that the square is given by x times y. That's the area. The height is dz. So dv is a times dz. What does that do? Okay, well, I'll just write it again. dm rho dv rho xy dz. And now I have this weird, awkward problem where I've got an x and a y. I got to get rid of them. One thing that helps me to know is that this pyramid has square cross sections. Square means x and y are the same. So x equals y. And then, look, this is the exact same formula I use for x over here. Why? Because it's basically an inclined plane. It's basically the same problem. I was lazy. I didn't want to have to find a new parameterization. But the idea is to illustrate that you can use it in 3 dimensions as well. Okay, so what do I do with this? I punch it into this formula. You may say, wait a minute, I thought there was an XCM and a YCM too. You're absolutely right. But look, by symmetry, I don't feel like calculating them. I know it lies somewhere beneath the center. The question is, how high up is it? If you want, set up the X and Y integrals and see that you end up with, L over 2, L over 2. Okay, so let's punch in this stuff into this integral and see what it looks like. Boom, it looks like this. So if you do this integral, you will find the center of mass of that non-uniform pyramid, which is nothing to scoff at. So if you know multivariable calculus, don't worry about any of this. Just set up your triple integrals, do your parameterizations, whatever you like to do. But if you haven't gotten there yet, right, it doesn't mean you can't do these 3D problems. What you want to do is slice. And the question is, how do you know when you can slice? Well, generally what you want to do is find slices that have constant density. So slice the object along planes of constant density. What does that mean? Here, the whole thing's constant density. So I decided to slice this way, but you may say, hey, isn't this constant density? Absolutely, it is. And we could have set up our integral with vertical slices instead of horizontal slices, and it would not have made a difference. For this guy, on the other hand, the density is not uniform. So if I tried to make vertical slices here, I'd end up with big problems because the density down here is not the same as the density down here. So the only slices I can set up in this one are along planes that have constant density, and this does not depend on x and y, and so I can slice along those planes. You can't do it on every problem. There's an infinite number of problems you can't do it on, but there's an awful lot that you can find that you can slice. Hopefully this video was more helpful than confusing.